All right, where we left off last time. We left off last time by talking about the different forces and how the different forces of nature. There are four forces of nature. One of them that we've experienced, and the other ones that are just there that keep us all alive. And so today we will be moving on to another aspect of physics that's important, which is energy. Let's see. One of the things I didn't really go into is like friction force, drag forces, and elastic stress and strain and stuff like that. But this is, we'll come to that if it becomes important. I mean, we've done some of this stuff, but it's not really that big of a deal, at least not yet. I will fold some of this into what we're talking about here. We're going to skip this chapter on gravity for the moment, and we're going to jump over to work, energy, and et cetera, and so forth. So these definitions, or these things, let me tell you what's really going on. You know, energy is the ability for stuff to do work, and what's work, and the work is the ability for stuff to expend energy. That's all fine and good, but what's actually happening here? So here's what's going on. You have, let's see, the ability for objects to move around. In order for objects to move around, we saw this with Newton's second law. In order for objects to move around, you have to have a force that you exert on it. That force has, okay, so you have a force like the electromagnetic force. So we have this thing, forces cause changes. Okay, so forces cause accelerations. They cause objects to move at a different rate. And with these forces, you're going to have an associated mathematical expression that tells you where this force comes from. It gives you the origin of these forces. Okay, so these mathematical expressions, they're different for each force, and they give you a quantity that we call the energy. So for each force, there's an associated formula that tells you the energy associated with that particular force. All right, the energy is just a mathematical expression. You write it down. It's some quantity that you calculate. Okay, let's see. So this is the first time I've explained it this way, but here we go. There are two different types of energy that something can have associated with it. And these are actually also related to the fact that with the coordinate systems that we talked about before, you can have a coordinate system with an arbitrary origin, right? You can choose the origin of your coordinate system. You can also choose the speed with which your coordinate system is moving. Okay, so any part of the coordinate system that is not where the origin is located or how it is moving at a constant speed in a straight line would mean that you have an accelerating reference frame. And rather than having a coordinate system that is accelerating, or like intrinsically a coordinate system that is accelerating, we would say the acceleration is caused by some force and not by an intrinsic property of the coordinate system, at least up until general relativity, which is not what we're talking about. So in the Newtonian framework, you can choose the origin of your coordinate system, you can choose the speed with which your coordinate system is moving in any direction, but as soon as that coordinate system rotates or changes its speed, then you would interpret it as a force and not as an intrinsic property of that coordinate system. With energy, there are two kinds of energies that we care about. One of them is an energy because of position, and the other one is energy because of motion. So I have a question here. Can I quantify the force of love? No, I can't quantify the force of love. That would require a different type of mathematics, I suppose. All right, so you have an energy because of the position where you're located, right there. So it's associated with this, and you have an energy that's associated with the motion. Now, bear in mind that when you choose a coordinate system, you're actually choosing an origin and you're choosing a speed of that reference frame. And so the energy that you get, whether it's from the position or from the motion, is actually somewhat arbitrary. You can choose a coordinate system where there's an origin such that the energy of that something has because of its position is zero. Or you can choose a coordinate system such that the energy that an object has because of its motion is zero. So you have a ball that's moving across the screen. So for example, you have, suppose that here's the ground, and here is a ball that's moving at a constant speed in a straight line like this. You would say, this ball has both potential energy, which is going to be mgh, and it has kinetic energy, which is 1/2 mv squared. However, because I have the ability to choose what my origin is and what my velocity is of my reference frame, I can transform this thing, this ball motion, into a coordinate system that moves along with the ball and where the origin is attached to the ball, such that it's got no height. So the height goes to 0 because now the origin is here, and the velocity goes to 0 because I'm on a reference frame that's attached to the ball. So energy, it's a mathematical formalism, or like it's a mathematical expression, but it's one that actually depends upon your coordinate system. So something useful to bear in mind. So each of the different forces, it's like there's only one kind of motion that you can have. There's only one kind of motion that you can have. However, there are different kinds of forces you can have, and there are different kinds of potential energies that you can have that are related to the energy associated with position. So what we call the energy that we have, so energy again, I'll write it down. We have the energy of position that we call potential energy. That says potential energy, and that says energy. So the energy associated with the position of something is like its configuration is called potential energy. The energy associated with the motion is called kinetic energy. Oh, these are Y's there. So potential energy is the energy associated with how something is positioned in your reference frame, and the kinetic energy is how something is moving in your reference frame. There's only one kind of motion. I mean, it's in 3 dimensions, but you can only move something with time. But the potential energy, how it's positioned, depends upon the environment, because the environment is what establishes what the positions are. So like what these different force fields might be that are acting on your object depends upon how you assign your coordinate system. Like for example, you have a gravitational field, gravity. So we've talked about the fact that gravity is one of these forces of nature. It has a field associated with it. When you have, so you have some gravitational field that points like this, then you have some object located in that gravitational field. It has some potential energy because it is displaced from your origin some amount in the presence of this field. And this is an object, because the object has mass, that object will couple to that gravitational field. So a couple questions. Does this only work for the observable universe? As far as we know, there is only the observable universe. We don't have any way of just talking about what happens in parts of the universe that aren't observable. And as far as superposition is concerned, superposition is when you have two things and you add them, two things basically that have the same units, you can add them together. So for example, you can have something that is in a superposition of, well, for example, if I have a wave that looks like this, that is a superposition of a wave that looks like this and a wave that looks like that. So I add these two things together, I get a superposition, which is the sum of the two. Okay, now back to what we were talking about. So I mentioned before, you have, at every point in space, you have a series of forces. And this is the first time the last time I drew this was the first time I'd ever drawn it. So it's so we're exploring this consequence of this representation of the universe. So at every point in space, you have a variety of different fields that can act on something. As far as we can tell, there are only 4 of them. Okay, so these are the 4 forces of nature. And you have a particle located at this position, and it's going to, it has some charge associated with it. And the charge that it has associated with it is its coupling to each of these fields. So this one up here could be gravity. You could have electromagnetism, the weak force and the strong force. If it doesn't have the charge associated with that force, then this particle is going to ignore whatever that field is. So for example, if you have something that doesn't have electric charge, it will completely ignore the electromagnetic field. If you have something that doesn't have color, then it will completely ignore the strong nuclear force. So at every point in space, you have all of these fields are there, and your object will do 2 things. One is it will couple to that field, and 2 is it will distort the field. If it has a charge, it will distort the field that's associated with that charge. So just like in Einstein's general relativity, you'll have a mass, and that mass will distort the space-time around it, but it also couples to the space-time. Like, it responds to the distortion in the space-time. The same thing is true with some electromagnetic field. Like, you have a charged particle, electrically charged particle. It will create a distortion in the electromagnetic field, and if there's an ambient electromagnetic field created by its environment, it will respond to that. So both of those things happen at the same time. It will both create a distortion in that field, and it will respond to existing distortions in that field. And that comes through its coupling to that field, whether it be mass for gravity, whether it be electric charge for electromagnetism, color, or weak isospin. See, are the fields layered, or is it easier just to pick it that way? It's easier to depict it this way. So all these layers are infinitesimally thin. At every single point in space, each of these fields is present. The question is not so much whether the fields are there, but rather what is the contour that the field has. And so that's what we're going to be talking about. So when you have like some field, so let's say that you have the electromagnetic field or something like that, or a gravitational field. The field is going to have some value. So we look at the field as a function of position. Okay, and so the field might have different values because there's going to be some charge here that's going to distort the field in this area. You're going to have a negative charge here that's going to distort the field in this area. And so the ambient, in this case electromagnetic field, is going to have some profile or some shape associated with it. And the energy that an object has is going to be, you define a coordinate system, you define your origin, and you place this object in this field, and it's going to have some energy associated with its location in this surface. So in this case, it's a one-dimensional surface, but the reality is it's a three-dimensional surface. Like it's all of space is going to be filled with this electromagnetic field. That electromagnetic field is distorted by ambient or like nearby charges, and then you're going to place a new charge in that field, and that field it's going to respond to the contours in the field. The energy that it has at a given location depends upon where you define what zero voltage means in this case, or what zero height means in the gravitational case. So now you place your charged particle in this field, and the way that the charged particle is going to respond is it's going to seek the lowest energy state that it can find, certainly the lowest nearby energy state that it can find. So this particle will tend to drift towards a minimum energy. Okay, so here's, in this case, you have this field. The energy is the charge that it has coupled to that field. So in the case of electromagnetism, it's Q times the voltage. This curve right here is the voltage. And the charge that you have is what is the charge associated with that particle, whether it's an electron and has a negative electric charge, or whether it's a collection of electrons or a collection of protons. And it will have a tendency to drift towards a minimum in that field. Now, how does it drift towards it? Like, what is it that causes it to move? Well, apparently what causes it to move is a force. And the speed with which it moves from one place to another is going to be dependent upon how steep the local field is. So in this case, the field has some slope associated with it. And this particle is going to experience a force that is in the opposite direction of the slope. So the slope is this way, right? The slope in this case is positive. And the particle is going to feel a force that is in the opposite direction of the slope. So the slope is positive, so it's going to feel a force that goes in the negative direction. So there you go. That you have this energy surface. You place some object in this energy surface. Now it has a defined energy, a well-defined energy, because of this mathematical expression that's associated with it. That particle is going to respond to that energy surface, and it's going to respond in a way that is opposite the slope. If the slope is positive, then it's going to drift in the negative direction. If the slope is negative, like here the slope is negative, it's going to drift in the positive direction. So the force that an object feels is going to be equal to the opposite of the slope on this energy surface. So the force is equal to, that's an F by the way, it looks like an E, but it's actually an F. The force is equal to the opposite of the derivative, opposite the slope. Okay, so that's what? D voltage dt or dx, something like that. The force is the opposite of the slope of this. And the steeper the slope, the stronger the force. If it's a really, really steep surface, then you're going to feel a very strong force. If it's a relatively shallow surface, then it's going to feel a relatively weak force. So this is something that's interesting. You have some expression for a thing here. This is called a potential. Potential. That says potential. And the slope of the potential gives you the force. Let's see. I think you have to have a mass in there, but do you have to have a mass in there? Force is QE. Yeah, okay, so this is, the force is Q times the slope. All right, so anyways, this thing here is called the potential. In this case, it's the electric potential. You could have a gravitational potential. And the potential energy is the product of the charge times the potential, so QV. If it's the gravitational field, it will be M times the gravitational potential energy, which is some quantity. If it's a nuclear force, then it will be the nuclear charge that you have, so whether it's a color charge or something like that, times the potential of that interaction. So the potential is some surface that's associated with some field. The force that you feel is the response to the changing by the response to the gradient in that surface. And it's dependent upon the position, like where you're located. The amount of energy you assign to something depends upon where you choose your origin to be. So if the origin is here, then you would say, oh, these have negative energy, these have positive energy. If your origin is down here, you say, oh, this has, everything has positive energy. It's just differing amounts of positive energy. And then the response of that system, the response of your charge-carrying particle is going to be in the opposite the direction of the slope of the potential. Okay, question. Let's see. Question. I may be off. If you consider mass as the curvature of space-time, I suppose you may consider, maybe considered zero when at that point is the frame of reference, similar to how potential energy is considered zero. So I don't know how to respond to that one. That would require. I'm not in a position to respond to that one. Let's see. Energy just depends upon your reference. Potential or kinetic just depend upon your reference. Yeah, those are both true. So the amount that you assign to something you have an additive constant that you can have associated with it. You can define zero voltage to be the ground. You can define zero voltage to be one of the prongs on the power outlet. You can define zero voltage to be 100 volts. It's only the difference in the voltage that actually matters. So it's not the actual energy that matters. It's the change in energy that matters. Okay, so it's just a force off in a different direction, which may come back into alignment down the road. Not sure what that's referring to. Here's a good question. Is there any observations of the laws of physics changing? No. So far there's been no observation of physics being different in one part of the universe compared to another part of the universe. So one could imagine that different parts of the universe have slightly different laws of physics. And we've tested that. We collectively, scientists, have tested whether physics is different in different directions or whether there's different regions of space that have different gravitational constants. And so far nothing has been shown that their laws of physics are different. As far as we can tell, the laws of physics are the same everywhere in the visible universe. That is what a potential is, and the energy is the product of, it's the coupling, the energy is the coupling of the potential, which is the shape of the field, and the charge of the particle that's interacting with it. All right, let's see, did I miss anything? So you could have a gravitational field, and then the object is going to respond to something in that gravitational field. You could have an electromagnetic field, and then you have a charged particle that responds with respect to that electromagnetic field. If you have a neutral particle, it can respond to gravity, but not the electromagnetic field. And so all of these things are basically just energy of configuration, energy of location, and those are all potential energies. All right, let's see. That gives us potential, and kinetic energy is just the energy that something has in motion. If you want to impart, okay, so let's take a look at an interchange now. So drawing this picture again, now we have an interchange. Let's say that this is a gravitational field. So a gravitational field looks like this because of the presence of different objects. And actually, do I want to? Well, let's just draw the same field that we had. So here's an electromagnetic field. So it's not a gravitational field, I lied. It's an electromagnetic field. So you have these different charges that are distorting the shape of the electromagnetic field in this region. You have a particle that's here that has some energy associated with its position. However, it's going to experience a force because there's a gradient in the ambient field. It will experience a force that pushes it in some direction, and it will start to move. And a consequence of it moving relative to the reference frame that we've chosen, so the reference frame we've chosen is stationary with respect to this origin. It's going to start moving, and as it starts moving, so now in this case, it's not going to roll down the hill because this is position and this is energy or potential voltage here. Well, I guess it does roll down the hill. In space, in the space that we observe, it's going to move simply straight to the left. In the space that corresponds to the voltage and the position, it's going to roll down the hill. But this is not vertical. This is not the y direction. Okay, this direction here is the voltage direction. More voltage is up, less voltage is down. So this object will experience a force. It will move in response to that force. So the force is the negative of the gradient. It will move in response to that force. And as a consequence, it will exchange some of its energy of position. So it has energy associated with its position, this potential energy, and it will exchange some of that potential energy for energy in its motion. So then you'll get kinetic energy in its response. So the force transforms potential energy into kinetic energy. All right. So there we go. That's basically energy. That was a lot faster than I expected it to be. Okay, now let's take a look at, so this is an example of a quantum field. You have electromagnetism that's creating this thing. Let's take a look at a more macroscopic thing. So let's take a look at a spring. So here is a spring. We're going to have it a horizontal spring because then we don't have to worry about gravity, because then some annoying student's going to be like, but what about gravity? And you're going to be like, shut up, I'm not talking to you. But you are talking to them, but you just want them to get off your case. In this case, the actual force that's going on here is, again, the electromagnetic force, because you're talking about the chemical bonds between all the different particles in the spring. So fundamentally, it's the electromagnetic force, but macroscopically, it's manifest as this spring force. All right, so now we have some position, some equilibrium position. We can assign our origin to this position. And now when you displace yourself from this origin in either direction, you are going to compress the spring and create distortions in the energy levels in the spring that the spring will try to resist. And as a consequence, you will experience a force that goes this way. You know, if you compress the spring in this direction, you will experience a force that goes in this direction. You're encapsulating all of the microscopic interactions into some local potential, and that, or some local force, and that local force is minus kx, where k incorporates the chemical properties, the binding properties of, and the elastic properties of the material. You have this force is minus kx, and x is the displacement from the equilibrium. So it's x minus x naught, where x naught is the equilibrium. Okay, so you can create an energy from this. You can determine what the energy is by simply remembering that the force is equal to, in this case, it's going to be minus k times the gradient of the potential. So what are we going to call the potential? Let's call the potential, I guess, phi, because I don't have a better name for it, dx. And so then you go, you say, okay, I can do this. I can multiply both sides by dx. I get f dot dx equals minus k d phi. And then I move k to the other side, and I've got this force times distance. So I integrate the force times the distance. For every little bit I add up, I'm going to add a little bit of potential to my system. So just like when you had this potential surface, and if you only have the gradient, if you only know what the gradient is, that says you only know what the force is, then the way that you find out how much energy you add to the system is by saying, oh, I'm going to displace a little bit in this direction, and I need to multiply by the opposite of that gradient, which is the force. So I multiply by the opposite of the gradient, and that's going to build up a little bit of energy. So I build up a little bit of energy by pushing. I push in this direction, I go up by the slope. So I push in some direction, here's a force, here's the direction, and I go up by a little bit of the slope. And that is how I add up the little piece of energy that I add to the system. So after displacing over a period, over some distance, I add up all these little bits of energy that I'm adding, that I'm contributing, and then I get a total energy at the end. In that case, when you do it here, you're going to get that the energy of the spring system is 1/2 kx squared. And this x is the displacement from 0. So it's 1/2 kx minus x naught squared. So that is a way of constructing an energy for something that isn't one of the fundamental forces. Is you say, all right, how does it respond when I exert a force over some distance? What is the gradient that I get associated with it when I try to displace it in some direction? And then you add up all those little pieces to reconstruct the energy. All right, let's see. What do we got going on? Let's see. The forces of nature change depending upon your energy level. For example, electricity in the weak force merges at a point. So that's a little bit different. So I'll talk about the unification of forces a little bit later. I don't know anything about quantum computing that's useful. Let's see. Okay, is this between one electron and the positive nucleus, the potential, I mean? Okay, so a question, is this between the electron and the positive nucleus? So it can be, it need not be, right? You can have just any arbitrary charge that can create the potential. So what you would say is, what's the fundamental building block of electric charge? Like, what's the fundamental unit of electric charge, which would be the charge on the electron or the charge on the proton? And then you can construct a field by taking those elemental pieces and stacking them together in some way. So the simplest electromagnetic interaction would be between two charged particles that have the minimum allowed electric charge. And you would say, oh, one creates a field and the other one responds to it, and the potential is described by the field generated by one of those two objects. Okay. Let's see, what else? So that ended up happening, like I said, this happened way faster than I expected it to. I thought it was going to take me longer to get through this stuff. Let's see, but you displace one particle in one direction, right? Yes, you take a particle, you can displace it in any direction, right? You have some charge here, it's going to have a field that moves in all directions, all three directions. And then you can take a particle and you can displace it in an arbitrary direction. And you can just add up the pieces. I displaced it a little bit in the x direction. I displaced it a little bit in the y direction. There's a gradient associated with each of those, and eventually that will add up to be the gradient that I had relative to the initial piece, like the initial charge that I had, to create, what is the energy that I get. But the important thing is that energy is based upon, the potential energy is based upon where you're located in your coordinate system and what fields are threading through your coordinate system. Okay, let's see. Now, if you sum up the potential of all the electrons, you get the potential of the atom. Yes. So the potential is, and this is something that's actually important, and it actually is one of the reasons why it's a lot easier many times to do calculations using energy instead of doing calculations using forces. Because the energy is simply how much, you have, here's your field, here's your coordinate system. The energy is simply how much coupling do you have between your object and this field at this location. So here's your location X, and the question is, what is the potential? What is the voltage at, in this case, the voltage at that position X? And I multiply that by the charge, QV. And it doesn't matter, all of these potentials, all these potential energies, so this is the electromagnetic potential energy, they just add. It is only a function of position. It doesn't ask what the gradient is. And that, the force asks what the gradient is, but the potential itself is just a number. And so what you can do is, if you have a variety of unit potentials that you can make, right? Here's a variety of individual electric charges, and you want to find what's the potential at some location. You just add up the potential from each of these four. You add them all up at that location, and then you're done. Because all that it cares about is what's the height of this field at that location. That's all that it cares about. And so all the heights add, and you just add them together to get that value. It's an air. So what's the low pitch noise that you have in the background? That is the fact that I work right under the flight line of the Las Vegas airport, and the wind is blowing in the direction where the airplanes are taking off. Airplanes are always louder when they take off than when they land, and so it goes. The runway is this way, and it flies right over the top of my office. And so welcome to the location of. It gets annoying. There are other things that get annoying as well, because the doors are kind of loud in the hallway as well. All right. So these are, but according to quantum mechanics, you can't pinpoint the position of an electron, right? That's a different issue. Let me come back to quantum mechanics at the end instead of right here. Let's see. Do I not, out of curiosity, do I kind of not hear it after a while? I hear it when I worry about it. When I not worry about it, I don't hear about it. All right. Now, here's something, this goes back to what we had in our first discussion about coordinate systems. The fact that we will choose a coordinate system where all of these locations, all the points on our coordinate system are equidistant, right? That's something that we choose ourselves. We want a coordinate system where every movement of some length in some direction is going to be uniform. And there are good reasons that we wanted to do that. But what that implies is if you were to shift the origin from here, if you shift the origin from this location to this location, then the coordinate system doesn't change. Like how you measure something doesn't change. But suppose, for example, you have we'll draw our same potential energy curve like this. But your coordinate system, in this case, it's the voltage. No, let's not do it that way. Let's actually do the spatial coordinate system. So the spatial coordinate system, what if the spatial coordinate system were to spread out like this? So the coordinate system that we're using is actually not uniform from one side to the other. The things are closer together here, and they're farther apart over here. So if we were to now take this coordinate system, so here's our position x that we cared about. Here's our position x. And we move the coordinate system's origin so that the origin is now at this location. So we've shifted the whole origin over by this amount. So here's our new coordinate system. It looks like this. And that's going to mean that our first tick mark, I guess, is going to be here. The next one is going to be here. The one after that's going to be here. The one after that, so I guess I'll do these darker, slightly darker. So here's the next one. Here's the one after that. Here's the one after that. Here's the one after that. And so at some position x that we might care about, we've actually, by shifting the coordinate system, we've shifted where x is located. So as we move our coordinate system to the right and we say, I cared about position x, now this position x has moved. It's actually moved. Hold on, let me draw this one more time so that I can do a slightly better job. Okay, so here's our original coordinate system. Okay, where the spacing is not uniform. Here's the voltage. So we have some curve that exists in space like this, and we cared about what was the voltage at some position. I guess I'll use this one right here. We cared about the voltage at some position x. Now I'm going to shift the coordinate system because I'm going to do a transformation of this coordinate system into a new one. That new coordinate system is going to have its origin located right here. So that means that the first tick mark is going to shift over like that. The next tick mark is going to shift over like this. The next tick mark is going to shift over like this. The next tick mark over here is going to shift over like that. So everything has been displaced from the original coordinate system to this new coordinate system, which means that when I say I care about what's happening at some position x, my new x is over here. This is now x is located here, which of course I drew this at the minimum, so it's not exactly what I wanted to have happen, but we're going to go with it. And so it's slightly different. It's now a different position on this curve. The curve didn't change. My coordinate system, how I map that curve onto my coordinate system changed. Okay, but now x is no longer the same location on the curve. And there's no real transformation that gets me, I have to worry about the fact that my coordinate system isn't uniform from one displacement to the next. So as a consequence, the amount of change that I have to worry about with my coordinate system depends upon where I'm located within that coordinate system. If the coordinates are right close together, I'll have to make maybe smaller changes. If the coordinates become farther and farther apart, I'll have to make different changes. And so when you have a non-uniform coordinate system, you have to have corrections associated with it all the time. There's not a simple transformation that gets you from one to the other. Let's try, let me see if I can come up with let me give you the counter example. If you have a coordinate system, on the other hand, where everything is exactly uniformly spaced, then, and here's your curve, then when you shift from one thing to another, you can undo that shift fairly easily. So if I shift from this origin to a new origin, okay, so that would normally shift me over to this location. Okay, the transformation back is fairly straightforward. I just say, oh, now instead of what I care about as my voltage at some position X, I'm going to transform that to some position X minus however much I shifted my coordinate system. So that I can do if these things are uniformly spaced. I can have a simple transformation that gets me from my old coordinate system to my new coordinate system. And in that, when I do this, then it doesn't matter where I am, like it doesn't matter which point I care about, I shift it by exactly the same amount and it will get me back to where I started. If, on the other hand, going back to what I had before, if I have a coordinate system where the lines are all non-uniformly spaced, there is no simple transformation that will get me from one position to another. Okay, it's a local transformation that can only happen at a very specific location on that coordinate system. There's no global transformation that allows me to say, oh, I'm going to shift my origin, and I can shift that origin, and it maps directly onto whatever my discombobulated coordinate system is. So there's something special about having a coordinate system where it is invariant. The spacing in the coordinates is invariant to translations. I can translate my coordinate system by any amount, and it doesn't change how the spacing of those coordinates, like what the spacing of the coordinates is. Here, if I transform a little bit, all of these spacings are different, and so I don't have an invariant transformation if I slide my coordinate system, my origin from one point to another, where I do in this coordinate system where everything is equally spaced. So the fact that there's something that stays the same when I can translate my coordinate system, this is a coordinate system that I impose on the system, it means something. It implies that there's some quantity associated with that transformation that stays the same. So if you can imagine having this thing stay the same, there's something physical associated with it that must remain unchanged in that direction. Okay, so what does this mean? So if you have a global symmetry in your coordinate system, that says coordinates. A global symmetry in your coordinates. So it remains invariant under some transformation of your coordinates. There must be something, then that implies that something stays fixed. Is fixed. That's it. Something is fixed. F-I-X-E-D. So if under some transformation, there's some preserved thing with your coordinate system, then that implies that something physical remains fixed. Something kinematic remains fixed. The mapping of your coordinate system onto the mapping of your physical system onto that coordinate system will have something fixed associated with it. Okay, that is, in this case, what you get is some conserved quantity associated with that transformation. That conserved quantity is momentum. Okay, so we've talked about momentum, that momentum is this quantity of motion that Newton came up with. When something has momentum, it has both a speed and it has, a speed in a particular direction, and it has a mass associated with it. And that if you want to change that object's momentum, you exert a force, and forces cause change in momentum. So the momentum that's associated with a particular direction, as long as your coordinate system is invariant under translations in that direction, then that momentum is going to be conserved. Okay, let's see. Thanks everybody for that raid. Let's see what we got. Let's see. Situations where you'd want non-uniform coordinate system. The question is, are there situations where you want a non-uniform coordinate system? The answer is yes. So you definitely would want, so in this case you have a uniform coordinate system, like the one that I was describing. But there are definitely cases where you have a non-uniform coordinate system. The best example of that is when you have a gravitational field. So according to Einstein, when you have a gravitational field, you no longer have a coordinate system that looks like this. Okay, so Einstein's gravity says, oh, in the presence of some mass, so here's a mass, your coordinate system is going to be distorted. And so if you go some height above that mass, your coordinate system is going to spread out. That's not what spread out looks like. Your coordinate system is going to change because of the gravitational field. The gravitational field is a distortion of space-time. It's a distortion of your coordinate system. And so when you have an object in this that couples to gravity, any object with energy, is going to move in this coordinate system in some direction. However, because that coordinate system is not uniform in that direction, then momentum is not conserved in that direction anymore. And because momentum is not conserved in this direction anymore, it looks like there's a force being exerted on that object, when in fact it's a distortion of the coordinate system that's causing it to happen, and not. So according to Einstein, gravity is not a force. Gravity is a distortion of space-time, which means it's a distortion of the coordinate system. And because it's a distortion of the coordinate system, momentum is not conserved in that direction anymore. And so an object will gain momentum to the outside observer, but it's simply moving through a coordinate system where the coordinate system is non-uniform. The coordinate system varies as a function of position. All right, let's see. Look at all that rating. All right. So, because we have 3 spatial dimensions and we generally will have coordinates where the coordinates are all uniform in each of those different directions, we're going to have 3 conserved momenta. You're going to have a conserved momentum associated with each of the 3 directions, x, y, and z. Okay, so now you have momentum in the x direction that's conserved, you have momentum in the y direction that's conserved, and momentum in the z direction that's conserved. And because of this, people say momentum is a vector. It's a vector because there is a conserved quantity associated with each of the directions. And so you just, because they all have the same units, you put them in the same mathematical structure and you say, here's this conserved quantity, it's a vector. In each individual direction, momentum is a scalar. Momentum in the x direction is a scalar in the x direction. Momentum in the y direction is a scalar in the y direction. Momentum in the z direction is a scalar in the z direction. It's only when you combine them into, some quantity some mathematical structure that you would call it a vector. The same thing, University of Wyoming, all right. The same thing, if you have a coordinate system that is uniform in the x and y directions, but is not uniform in the z direction, this is what you get with the gravitational field. Then momentum is not conserved in that direction anymore, and so you would have conserved quantities in these 2 directions, and it would look like the object is accelerating. Its momentum would be changing in that direction. So the same thing can happen. We also have a time coordinate because the space-time that we live in is both the spatial position that we have and the moment in time that we have. And so there's a momentum that's associated with the time coordinate. These are all associated with spatial coordinates, but there's a momentum associated with the time component. And that one is energy. So because we have, not only do we have some spatial direction, but our clock, if we have the time direction, let's say that this is the spatial direction in the vertical here, and then time is in the horizontal direction. Because our time coordinate, our clocks all have equally spaced, like the second is defined in terms of like the number of oscillations of the cesium atomic clock. Because the time direction, if you shift back an hour, when we go to daylight savings time, the separation between individual seconds does not change. So the second today is the same as a second tomorrow. Because that doesn't change, that means that there's some conserved, there's an invariance in the system under translations in time, which means that there is a conserved quantity associated with this time translation. and that conserved quantity is energy. So you have momentum for the spatial directions, so those are space, and you have energy is conserved in because of our symmetry in time, because time translation doesn't affect the physics of the system. So you can, t minus whatever, t minus yesterday is going to give you the same physics today as t minus tomorrow does. And because of that, energy is conserved. Now, this is something that's important because energy is conserved only insofar as time is invariant. Like this, an individual second is the same today, tomorrow, and forever. If the time coordinate, if we had, we chose a time coordinate where the time coordinate were to spread out, then energy would no longer be conserved. We could still have an energy, we would still define an energy, but it would no longer be a conserved quantity because it no longer has this symmetry associated with it. It no longer preserves translation in time. So one of the things that you hear in lots of physics and things like physics discussions is that momentum and energy are conserved. Momentum and energy are only conserved if you have a coordinate system that is uniform in all the spatial directions and the time direction. If you change the uniformity properties of the spatial directions, then momentum is no longer conserved. If you change the uniformity of the time direction, then energy is no longer conserved. So energy and momentum are, they're conserved, but the reason they're conserved is because we indoctrinate all of our children to use coordinate systems that have equal spacings in all directions. So some people lose energy when they change the daylight savings times. That is true. Let's see, that's why movement along an orbit in space is nothing but a free fall through distorted coordinate system, according to Einstein. Yes, that's correct. All right, let's see. Is a logarithmic scale a distorted coordinate system? Yes, a logarithmic scale is a distorted coordinate system because when you have a logarithmic scale, you are looking at each thing here is a factor of 10 larger. Okay, so like here is a logarithmic scale would be like, instead of having 1, 2, 3, 4, 5 like this, it would be 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and so forth. So it is a fairly significant distortion of the coordinate system, going from basically 1 to 10 to 100. So each spacing is a factor. It's a constant factor instead of a constant difference. So this is basically an exponential or a geometric progression where each tick is 10 times the number, 10 times the tick. So 10 times larger than the one before it, 10 times larger than the one before it. So it's a geometric transformation to the axis. And this is an arithmetic transformation to the axis, where each tick is 1 plus x. So you go to the second tick, now you get 2. You go to the third one, you get 1 plus 2 is 3. One more is 1 plus 4 is 4, or I'm sorry, 1 plus 3 is 4, and so forth, where in this case it's 10 times 2 is 100, 10 times 3 is 1,000, 10 times 4 is 10,000. So that's a fairly significant distortion in the coordinate system when you do these logarithmic, some kind of logarithmic thing later. In the meantime, let's move on to the transfer of energy from one type to another. All right, I apologize for my inability to adequately express myself when it comes to those things. And we're going to move on to what happens when you have energy that is transferred from one form to another. So we see from the time translation invariance of our coordinate system that energy is conserved. So, and there are different forms of energy. You have kinetic energy, which we've already seen, and you have every force has its own potential energy. So you have an electromagnetic potential energy, you have a nuclear potential energy, you have the weak force potential energy, you have gravitational forces potential energy. All those potential energies, they all contribute to the same total energy of the system. So it's the energy of the motion that you have because however your coordinate system is located. You also have the energy associated with your position in that coordinate system. So that is a conserved quantity. The sum of all these things is a conserved quantity, which means that you can share it between them. So this is something that's kind of interesting to consider. you have all these, it's the energy that's conserved. It's the total energy is the sum of the kinetic energy plus, whatever all the potential energies are that you might have in your system. This is the thing that's conserved. None of these things are conserved on their own. It's the sum that is conserved, not the individual components that are conserved. And so what that means is you are free to slosh these things around between each other. You're free to take the kinetic energy and convert it into some form of potential energy and vice versa. Okay, the way that you do that, the way that you transform energy from one type to another is by responding to the forces. Okay, right? Forces cause masses to accelerate, and that the force is the gradient in the potential, and that creates the kinetic energy. Or if you have a gradient and a potential and you give something some kinetic energy, you can convert that kinetic energy into potential energy. So it's the energy that's conserved. So all of these things are kind of degenerate with each other. All these representations of energy are degenerate with each other. You can move them from one type to another. This is not something that you can do with momentum. Momentum has, the momentum in a given direction is conserved based upon the coordinate system, but there aren't, momentum is mass times velocity. There's no fundamental force associated with these momenta, right? There's no force associated with, there's no fundamental force like electromagnetism or gravity that cares about the velocity. Ooh, that's an interesting thing. I'll have to think about that. So there's no fundamental force that depends upon the velocity, like the electromagnetic force doesn't depend upon the velocity. And so as a consequence, the momentum, there's no other form of momentum. It's not like here's the electromagnetic momentum and here's the gravitational momentum. There is only momentum that's related to the coordinate system. In the case of potential energy, because you have this coupling to all these different forces, there are different forms of potential energy, and it's the sum of all those potential energies that gets conserved. So when we're talking about the magnetic force that's proportionally to the velocity, so there is I guess one caveat is when you go into electromagnetism, which will be later, there's the Lorentz force, which is QV cross B. So this is the force that a charged particle is exerted. This is the force that a charged particle feels when it's moving in a magnetic field. Looks like this, and this is a force that it depends upon the velocity. However, there's this very special form. There's an equation that is satisfied. The actual description of this conservation law thing that I described, where if your translation invariant if you translate your coordinate system, then you get something that's conserved associated with it. It's conserved up to some mathematical expression. And that mathematical expression has to have a particular form, and this force law has that particular form. So it's similar to, say, adding a constant to something doesn't change anything. It's adding an expression, adding a force that has this very specific form that that makes what my statement still true, even though I left out that detail. So this is a detail that will be covered at a later time. Okay, so we come back to this thing where it's the energy is conserved, and because you have all these different forms of energy, it's shared among these components. That's important. Okay, so how do you transfer energy from one type into another? The rate at which energy gets transferred from one type into another is the power. So power is the rate of how quickly energy gets transformed from, say, kinetic energy to potential energy is power. So another example of a way of transforming energy would be to, say, take the kinetic energy and transform it into electromagnetic energy in the form of radiation. So let's say that you have a bunch of objects, like here's a bunch of atoms that are all bouncing around. They all have kinetic energy. So you have these atoms that are bouncing around, bumping into each other. And a consequence of them bumping into each other is that they produce photons. So then you have, now you have photons that come out of this, because random motion of things is temperature. The higher the temperature, the things your massive stuff is going to start to glow, and you are going to radiate energy away, and that radiation carries energy with it. So you have a photon or light coming off of this, and photons have energy, they carry energy. So you're transforming kinetic energy of the motion of like a filament in a light bulb into electromagnetic energy. The rate at which you transform it from one type to another is the power. and that power is measured in watts. So if you have a 100 watt light bulb, it's transforming 100 watts of energy per second. I'm sorry, it's transforming 100 units of energy, 100 joules of energy per second into photons. So watts is the energy per second, how quickly some energy is transforming from one type to another. Okay, another example would be energy that's in one form of kinetic energy. So say you have a wheel. So here's a wheel that's moving around. A wheel that is spinning has kinetic energy. It's energy because you have little pieces of mass that are moving, in this case in a circle, but it's still motion. It has kinetic energy. There's a way of describing it that makes it so that it's rotational energy that's somehow different, but it's only different from kind of a generic point of view, like an abstract point of view. Fundamentally, it's the same. It's the instantaneous motion of all the particles in that wheel. But you have some form of thing that's spinning, some energy that's spinning around, and you want to translate that into some horizontal energy. So say you have a spool, like this is a spinning wheel and it has a spool associated with it. This is going to have some energy and it's going to drag something along or like lift something up like a garage door, and it's going to do it at some rate. And so you'll have like a half a horsepower. A horsepower is the equivalent of a watt. It's the same unit as a watt, except that it's like 1,000 watts per horsepower. So 1 horsepower, I think it's like 760 watts, something like that, which is like 1,000. 760 is about 1,000. So if you have a 1 watt garage door opener, it is imparting some of that kinetic energy into raising the garage door. Now there's a bunch of friction, so it gets dissipated, but you can translate the rotational energy that something has into kinetic energy that something else has. Another example would be lighting, a calorie. Calorie is also a unit of energy. I don't remember what it is. It's a single calorie, like a food calorie is 1,000 calories, which I think is 4,000 joules, 4,100 and something or other joules. So it's about 4,000 joules. So if you eat a cookie, let's say that you have a cookie that is, it's a chocolate chip cookie. And so the chocolate chip cookie is going to be, something like 200 calories. How quickly can you eat a chocolate chip cookie? So you're taking the energy in that chocolate chip cookie and you're putting it into you're kind of storing it in the chemical interactions that are available in your body into ATP. You can eat a cookie, let's say, in 10 seconds. All right, 200 calories, that's 4,000 joules. Let's say that it's 5,000 joules just to make life easy, or we can say that it's 250 calories, either way. Or 225 calories. So we multiply these things together and we get what? 100,000 joules in 10 seconds. That gives us, when we eat a chocolate chip cookie, if we eat it in 10 seconds, we're looking at 10,000 watts. So we're transforming energy or transferring energy from one place to another. In this case, it's chemical energy associated with the chemical bonds, at the rate of 10,000 watts. So that's pretty gnarly. Okay, so if you really want to see how fast something transfers energy. So in this case, you have energy and chemical bonds. What are chemical bonds? Well, so you have a hydrogen atom here, you have a hydrogen atom here, maybe there's a carbon atom associated with it, there's a carbon atom between it. So you have these double bonds between, of course I drew them as oxygens. They look like oxygens in that case. So you have a hydrogen bond to a carbon like this. That's what a hydrocarbon looks like. And then you'll have a chain of carbons. I guess it'll look something like that. And then you'll have another hydrogen here. So all of these things have different bonds associated with them. Those bonds have energy associated with them because you have this potential that's, you have a positive charge here. You have an electron, so you have this positive negative charge. You have the positive negative charge nucleus here. You're going to create some kind of profile that the electrons are going to like to live in. There's energy associated with that. That's the energy that goes into the bonds. If you want to break those bonds and rearrange them, so say you have a hydrogen bond that looks something like this, and then you have an oxygen that comes nearby. The oxygen might be a deeper well. So here is the hydrogen to carbon bond, and here is the hydrogen to oxygen bond. And you have a hydrogen atom that's sitting over here saying, like, I'm happy in this bond that I have right there. What you then do is you say, well, I'm not happy with you in that bond. I'm going to raise the temperature I'm going to raise the temperature so that now this hydrogen, or this electron that's associated with the hydrogen atom, is going to be sloshing around in this potential. I raise the temperature, so I'm raising its energy. It's sloshing around, it's got more and more energy, and eventually it can overcome this barrier that's preventing it from binding to the oxygen. Once it binds to the oxygen, it's going to release that much energy left over. It's going to have that much more energy that it can give up. So it starts with some amount of energy in the hydrogen-carbon bond. It's hard to just break that bond directly. Well, just bringing an oxygen nearby isn't going to break that bond on its own. What you have to do is you have to add some energy to the system, increase the kinetic energy, which is going to cause this bond to, stretch and so forth, which is mathematically would be shown as like raising the energy of the particles in there in order to make it over this hill. Once you make it over the hill, now it's able to bind to the oxygen, and the oxygen bond is stronger than the carbon bond, and so you give off this much energy by transferring the hydrogen bond from a carbon to an oxygen. And then this comes off, and then you say, look, it's fire. So fire is, in this case, you take the oxygen in the atmosphere, you take the hydrocarbon bonds in your fuel, you heat up the fuel by some mechanism, and then you have the oxygen nearby, and the oxygen will come in and it will take the place of the carbon in these bonds. And you will produce what? You produce two different kinds of bonds. You'll produce carbon and oxygen bonds, CO2, and you'll produce oxygen and hydrogen bonds, H2O. Okay, so I guess we do it this way, H2O. So you produce these bonds and you produce these bonds, and that's all from the fact that these bonds are more tightly bound, and so you get energy released in that. Okay, so what did this have to do with anything? I'm sure this had to do, this was a bit of a distraction, and it had to do with something that we were talking about. What were we talking about? Oh, so the bonds that you have in, the chemical bonds that you have, it's a potential energy associated with the electromagnetic field, and you can release that energy by associating it with a different bond that is more tightly bound. So you give up, you can extract this excess energy by switching the bonds from the carbon bonds to the oxygen ones. If you want to go backwards, which is what plants do, if you want to go backwards, you have to add this energy back in. So there's oxygen in the atmosphere, or there's carbon dioxide floating around in the atmosphere like this, and you want to undo this process. You want to take the carbon and remove the carbon from the oxygen and put it back into a hydrogen-carbon bond. So you want to take this carbon and put it back into this kind of structure. The only way you can do that is by having an outside source of energy that can supply this difference and flip you back over that bump. And so that's what photosynthesis does. Photosynthesis, it's a long process, but it basically takes energy from the sun to provide this, and then it runs this burning process backwards, takes the carbon out of the carbon dioxide and puts it back in to the hydrocarbon bonds that make up the structure of the plant. Okay, so you have these potential energy associated with these chemical bonds, and you're transforming it into kinetic energy in the case of like a gasoline engine. So you have hydrocarbon bonds, you have a gasoline engine right here, it's got a cylinder, and you put that chemical energy into here. That chemical energy fundamentally is the chemical bonds, electromagnetic force. And then you're driving this piston up and down and up and up and up and down and attaching it to some kind of crankshaft that's going to spin around and then drive the car. When you fill up your car with gas, you're doing like a gallon, 1 gallon, which is like, it's a gallon like every 4 seconds. So let's say you have like 1 liter per second. Okay, and how much energy is there in a liter of hydrocarbon bonds? So a single liter of hydrocarbon bonds in a liquid form is something like 50 megajoules. 50 megajoules per liter. That means 50 megajoules per second is going, when you're filling up your car with gas, 50 megajoules per second. And so the rate at which you're transferring power, or what eventually will be power, so in this case, power is the transfer of energy from one location to another. So I guess it's apt. It's appropriate to describe it this way. The rate at which, the power with which you're filling up your gas tank, the rate with which energy is transferred from the gas station into your car is 50 megajoules per second. 50 megajoules per second, that is 50 megawatts. 50 megawatts is like a small municipal power plant. That's the rate at which, so a typical home is a kilowatt. This is like 50,000 homes. It's the same rate that power is being consumed by 50,000 homes. Right, one home is about 1 kilowatt for a kind of a smallish home is about 1 kilowatt. And so this is 50 megawatts. And so that's 50,000 homes. Wow, that's fast. That's why we use gasoline. 50 megawatts. You're charging your car basically with 50 megawatts. That's fast. All right. So, anyways, that's what power is. When you hear, how do you convert energy from one form to another? That is the fact that energy has all these different forms. They're all degenerate with each other, meaning they all have the same kind of units, and so you can shift things around. And the process of doing so is like the rate at which the energy transforms from one form to another is power. So there we go. So in order to feed a generator that produces electricity for a small town, you have to keep pumping gas at 1 liter per second. Yes. So another way to think about this that's kind of related to that, just thinking of, so this is an aside, but unit analysis. So let's take a look at units. This is a fairly substantial aside, and we'll call this the Q&A section, and I'm going to ask this question. So I think that'll be it for as far as new material is concerned, because I need to think about some of this stuff when it comes to the non-conservative forces, and come back to it next week. But looking at units, you have so miles per gallon. That's miles divided by gallons. Gallon is a volume, so this is a length. Miles is in length. Gallon is length cubed. And so the units of miles per gallon is 1 over length squared. That's an area, 1 over area. And the way that this was first described to me is, what does miles per gallon have to do with inverse acres, right? An acre is an area. And so miles per gallon has the same units as 1 over acres. It's got units of 1 over area. That's weird. It's weird to think about miles per gallon as having units of 1 over area. What does that? But that area must mean something. What does that area mean? It has to mean something. It's got to have some significance to it, because miles per gallon has some significance to it as well. Miles per gallon is how many miles you can get out of a single tank or a single gallon of gasoline. And so the area that is described here, the fact that miles per gallon has units of 1 over area, that area has to somehow mean the same thing. It turns out what that means is, if you were to take a tube, here's a tube of gasoline. Here's a tube of gasoline. And here's a car, and it's a special car. Here's a special car. It's got a little intake right here that as the car drives, it will scoop up the gasoline in this tube at the rate that it's driving. Okay? The area in miles per gallon is the cross-sectional area of that pipe. And the way to think about it is, okay, suppose that you have, let's say, 25 miles per gallon. Okay, so that means you can take 1 gallon of gasoline and put it in a little pipe like this that is 25 miles long. Okay, so you have a 25-mile long straw of gasoline and 1 gallon in that gasoline. And so then the question is, what's the cross-sectional area of that straw? And that's what miles per gallon is. This gives you the cross-sectional area of that straw. If you drive a car 25 miles along that straw, you will slurp up the gas as you go. So let's see. So there's a question here that is not sure about this. There's a little error in that the household usually accounted for in kilowatt hours. Yes. So kilowatt hours is the unit it's a unit of energy. So when what you're charged for in your home is the amount of energy that you consume, and not the power that you consume is the instantaneous transfer of energy from the power company into your house. So if you turn something on that's like, say, a 1,000 watt space heater or microwave oven, you have a 1,000 watt microwave oven, you turn it on, that means that 1,000 joules of energy are being transferred from the grid into your house and into the microwave oven. So the question is not at what rate is the energy transferring, because it might be instantaneous. Maybe you microwave something for 1 second. But the total amount of energy that you consume is what you actually get charged for. And so energy is equal to power times time. So power, remember, is the rate at which energy is transferred. And so if you just care about the energy, then you need to multiply the power. It's like, this is like distance equals rate times time, right? Distance equals rate. Power is a rate times time. Okay, except now instead of distance, it's energy. Power is the rate and time is the same. And so what is the time that the company cares about? Instead of measuring it per second, they measure it per hour. And so you get a kilowatt, which is a rate, times time, a kilowatt hour. And so if a typical house will, at 1,000 watts, at 1 kilowatt, will have 24 kilowatt hours of electricity that it consumes in a given day. And so that's what you get. Is that why they're trying to ban fuel vehicles in California, because straws are already banned? That's a good question. I cannot explain nor justify some of the decisions that California is making when it comes to their electricity generation and it doesn't always make sense. In particular, the fact that they're shutting off their single largest source of green energy in the state, and they're doing it early because it makes people feel good about themselves when they don't understand what they're talking about. Let's see. Is there only kinetic and potential energy? Yes, there's only kinetic and potential energy. One is associated with the position, the other one is associated with the velocity relative to a coordinate system and the ambient fields that exist in the coordinate system. Position, fields only depend upon position. The electromagnetic field has a value at positions in space. And the same thing, gravitational fields, it's an energy associated with their positions. There's no gravitational field with motion, at least not in the physics that we're looking at. Let's see. But the energy is only conserved. Energy is only conserved for in coordinate systems where the spacing is equal. Well, in this case, the time coordinate is equal. Let's see. I was amazed how a data physicist always solved my mechanical engineering dynamics problems using conservation of energy. Yeah, conservation of energy is a big deal. In fact, in chemistry, they talk about conservation of mass, right? You'll be like, oh, what's the mass? If I have 5 kilograms of something and I split it into 2 pieces and one of them is 4 kilograms, then what's this kilogram that's left over here? How much is left over here? And the answer is 1, like the question mark kilograms. That's conservation of mass. Conservation of mass is another manifestation of the conservation of energy, because energy is equal to mc squared if it's a stationary object. And so the fact that mass is conserved, that's only true. Mass is conserved only in a situation where this equation remains true. This is actually not the whole equation. Einstein's actual equation is E squared equals, if we set C equal to 1, it makes it a little bit easier, is m squared plus the momentum squared. The total energy of a particle, according to Einstein, is the square of the mass and the momentum. So the kinetic energy and the mass energy is the total energy of the total kinetic energy of a particle is the mass part and the momentum part. And so conservation of mass only works when you ignore the momentum. If you can somehow transform mass into momentum, if you can make this transformation from mass into momentum, then mass is no longer conserved. You can have a radioactive decay of some particle, it will split into 2. The sum of the masses of the outgoing particles, the daughter particles, will be less than the mass of the parent particle. And the difference being made up is energy that's gone into the kinetic energy. So this equals mc squared only applies when there's no momentum in the system. let's see. All right. So that gets us to power. We'll come back and revisit the non-conservative forces thing, and then we'll also move on to gravity. What do I have? I'm pulling up this thing. So we did power, work energy power, and world energy use. We'll talk about world energy use at a different time, and where that comes from. So, but next time what we'll do is go into non-conservative forces, which is friction, drag forces, and stuff like that. And then we'll start talking about probably momentum. And then we'll go into, then what we'll do is we will pick a force. So typically the way that these textbooks are organized is that it lays out the framework. So we saw that you have a unit system, you then have a mathematical map, you have a mathematical coordinate system, you map your unit system onto that coordinate system, and you learn how to translate physical world onto your mathematical model. That's kinematics. Then you add the forces into the mix, and that gets you the dynamics. How do you move things around within that coordinate system? And then you look at what are some of the properties of your coordinate system, like it produces conserved quantities, like energy and momentum. And one thing that we haven't yet discovered, discussed, is the angular momentum. And then the book will march through, okay, let's look at gravity first, because gravity is kind of the simplest. So you take a look at gravity, and then you say, what are the consequences of the gravitational field, given the fact that we know that it has energy and stuff like that? And then the next thing that you'll do is you'll go from here, you'll start talking about, all right, now let's see kinetic energy. So heat and heat transfer and all that stuff is kinetic energy. Like the thermal motion of something is the low scale kinetic energy. Then you go from there into electromagnetism. So you say, now let's take a look at the electromagnetic force and how does it relate to energy and all these other components. And then only at the very end, you get just a couple chapters on nuclear physics. And looking at, you get nuclear physics, you have one chapter for all of nuclear physics, which is half of the forces. But that's how it works. That's the world that we live in. So those are whole books on their own, like nuclear physics and stuff. So that's kind of how these things are organized, is that now that we know that there are these forces and that those forces have an associated potential, and that potential is able to, you have these four fields. Those fields create some potential. The gradient of that potential gives you a force, and so those are the four fundamental forces. And then looking at what are the consequences of that force. It's the way that the thing unrolls.